Good morning to all of you. So for 2-3 minutes, please go through whatever I have done last class. And if you have any questions, doubts, you can ask. Transfer, yeah. Yeah, okay. So the question is about, so I think, are there any other questions? So this question was about, actually no, we discussed about frame element. So the frame element means when you have axial as well as transverse load, then you will have to basically model the structure using frame element. But then when to use or how to distinguish between the use of truss and frame element. So see, we have also talked about modeling truss, planar truss structures or 2D truss structures. So see, if the in a structure there are different members and they are connected by pin joints. So all the members, say this is the one member, this is another member, and maybe there are multiple members. And for the timing, let me just take this as an example. That suppose you have this situation. And say there is usually what we do is in case of truss, of course, we consider the forces at the joints. So if there are any distributed forces also, we approximate them, take at the joints. So you can say with respect to this member, these two forces will give rise to axial as well as the transverse force. Similarly, for this also, these two external forces will give rise to axial as well as transverse forces. But so then whether we should go for modeling this using frame element or truss element, that's the question. So see, in this case what happens is, because this is connected through the pin joint, and the joint here is also a pin joint. So see, the pin joint, that is this member and this member, they are free to rotate relative to each other. So there is no moment transfer from one to the other. So what would happen is, ultimately the loads are going to be resisted by the development of axial forces in these two members, axial force here and axial force here. So this structure then you model using a frame element, but the truss element. But suppose this is either it is fixed at one of these ends. So the same structure, you can have different variants. Say that is this is one and this is the another structure. See, either even there is a pin joint here, there is a pin joint here. Let us say we have a situation, but let us say now this is fixed here, and you have a transverse force in the vertical and horizontal direction at that location. See, now what will happen, the moment have this joint here, and we are assuming that the joint is frictionless, so it is free to rotate. There is no bending moment throughout in this member from here to here. But the moment you fix it here, then there is going to be, because when whatever forces are coming in the horizontal and vertical direction, and of course here whatever components are coming, their resultant is always going to be in this direction. For this, it would be actually in this direction. But the moment you fix it here, it is not free to rotate. So because of these forces transmitted to this, there would be reaction moment here, leading to bending moment, some distribution of bending moment throughout the length of this member. So then in that case, this has to be modeled using frame element. This is still is connected through the pin here and it's pinned here. So this you can still model using truss element. Or you have this joint, but the connection here is you make it as a rigid connection. Say let's say these two members are welded. Once you weld these two members, there is no longer relative rotation possible between these two. So obviously to constrain that relative rotation, there would be moment there. So there is going to be bending moment. And therefore then again you'll have to consider the modeling both these members now using frame element. So the truss means you have to basically make sure that the member is undergoing only axial deformation. Although when it deforms, it might rotate little bit, but still this will not bend, means this will remain. If it was initially straight, after the application of the force, because all these joints are here pin joints, So this will remain straight, this will remain straight. It might, as a rigid rod, it might rotate, and then it might get compressed or elongated. But if it was initially straight, it would remain straight. But here, if this is the situation, either these are rigidly connected, or here, there is a pin joint, and this location it is fixed. So then you will find that this member is not going to remain straight, but it's if you try to draw the center line, it would actually take some shape like this. So there is a change in the rotation of the member along the length of the member. So in such situations, you'll have to model the structure or the component using frame element. So essentially, ultimately it is, if there is a bending resistance, so there is a bending moment coming onto the structure in addition to axial force, then you need to model using frame element, otherwise you can use truss. Yeah.
So suppose the first problem we model with the beam element,
yeah.
Frame element, then what will be the effect on the result?
Then what you have to do is, if you still want to model using frame element, that's another good question. So you can model, let's say you want to model this using frame element and this using frame element. And if you do the usual assembly procedure, that let's say for the simplicity that we model this using one element, this is also another frame element, and this is global node 1, 2 and 3. So if you do the assembly as usual, then what you would be doing actually would be now enforcing the continuity of rotation of this member and this member at this point. So then you will not really be simulating this pin joint here, which allows the relative rotation between the two. So then what you can do is, you have to have two nodes here, duplicate nodes there, and those two nodes you have to say that the x and y displacements are the same for both the nodes, but the rotations are different. So then you have, if you still want to model using frame element, you model this using, say this is node 1, this is node 2, and the other member you model, say this is node 3 and this is node 4. These are global node numbers. This is element 1 and element 2. Since at this point, in case of the frame problem, there is a pin joint here, so the relative rotation is allowed. So theta z of this node cannot be same as theta z of this node. So only what, of course, these will move together along x and y direction. So then you have to say that u naught of 2 is equal to u naught of 3 and v2 is equal to v3, but theta z2 is not equal to theta z3. So now if you do this, that means you couple these 2 degrees of freedom of these two nodes, but leave the theta z, then you can simulate this truss problem using frame also. But if you do you have a single node there, so the moment you have a single node means you are inserting that all the primary variables, that is element nodal degrees of freedom, uv and theta z, they are continuous, and once you say theta z are continuous, you are saying there is no relative rotation between these and this, means you are fixing them, you are considering as if they are welded. Okay, so this is what you actually would have to do if you want to model the same problem using frame element. That's a truss problem modeling using frame element. Okay, so are there any other questions? Yeah.
And that we are solving first finally.
Mm-hmm.
So we will appreciate the problem better if we know which physical system it is representing and we do application for.
So that's how, see, that's how we are actually going physics-based element discussion here only, no? Like a truss element, beam element, frame element. So it's more like we are not just taking differential equation, but we are talking about that in mechanics. If you have a problem where there is axial load, or you have a structure where there are only axial deformations, then you model using truss. If you have axial as well as transverse loads, model using frame element. Then we also said the beam should be thin, then you can use Euler-Bernoulli beam theory. If the beam is not thick, then that's what we started with, Timošenko beam theory. And a real structure means then you have to see the things around, and we can always think of, like when you enter towards the IRD main building, so you see that structure inside. So you think of, if you want to simulate using finite element, what you need to do. One needs to do to model that, and like that, you see things around and think of modeling those structures using finite elements. So you want to use truss, beam, frame element, or subsequently we'll discuss 2D. So we'll see how we can model these structures. Okay. So it's more of, I think, physics based, but of course more real life problems means you should actually think of all the structures which is say around, and then you can think of you can always think of whatever you have learned, whether you can model this structure using these elements. So is there any other question? Okay, so then let me start with what I was doing in the last class. I had started with, so Timosenko beam. What I will do is actually beam and frame I will combine together, so we will have everything in this, although I am writing it as Timosenko beam element. So what now we are going to do, see, when I started with Euler-Bernoulli beam element, that time I said this is for thin beam, that means the length is much larger compared to the representative cross-sectional dimension like thickness. So that is what we had said for the Euler-Bernoulli beam element. Now here we are saying that the Timosenko beam means it's basically a moderately thick beam, and this actually means that if your L by H is something less than say let me put 20, then you need to consider Timosenko beam element rather than Euler-Bernoulli beam element, where L is the length, so that is what I am talking about. H is representative dimension, it can be diameter if it is a circular cross section. So if this is the total beam, length is L and representative cross sectional dimension is H. So if this L by H is less than 20, then Euler-Bernoulli beam assumption may not be accurate, and then you will have to relax the assumption in main assumption in the Euler-Bernoulli beam theory, that is normal remains normal to the middle surface after deformation. So this is what I started in the last class. We call such beams as moderately thick beams, and so I was talking about how will it deform. So what I was saying in the last class, let me draw a little bigger picture so that I think we can. So this is the undeformed configuration, and say after the application of the load, let's say the right end moves relative to the left. So let me draw the deformed shape. So it takes a shape like this, and say this is your middle surface here, and this is the deformed middle surface, goes like this. So if I consider initially normal to the middle surface here, let's say this, and this normal finally moves to this configuration here, and say that let me first draw the tangent to this deformed configuration so that I can demonstrate it more clearly. So this is the tangent here, and at this particular point, and say the normal is this is the normal. But what I am saying, now this normal does not go along with this, but it actually is at some angle with this. So actual normal, that means initially we draw this line here in the undeformed configuration. That line goes to this particular configuration here like this. This is straight, actually straight line, so although I think it comes out as a curve the way I have drawn. So this is this line, the blue line actually goes here, whereas this is green one is the normal to the tangent drawn to the middle surface or the neutral surface at this particular location. In case of Euler-Bernoulli beam theory, we had said that if you draw this normal in the deformed configuration, this is going to coincide with this green line. That means this green line here is at 90 degrees to the neutral surface. So now it is no longer 90 degrees, but it is at some angle, and say if I draw another vertical line there, so if I draw let's say a vertical line here from passing through this point, so this is the vertical line here. So now there are various rotations involved, as you see. This is because this is green line is normal at 90 degrees. So this rotation for a small deformation case would be dv by dx. But actual normal has not rotated that much. That means actually this line if you take and if you look at this angle, the angle between the vertical and this red line which was initially here. Now this line has gone there, this one. So let us say this angle is, now it's no longer in terms of V, but let us say that is some angle theta z. Rotation is about z axis. So the coordinate axes are, this is x and this is y. So theta z is the rotation about z axis. So now this angle between the normal to the middle surface in the deformed configuration and the line drawn in the undeformed configuration which has gone here in the deformed configuration, no, that is this angle. This particular angle is now the difference of, so as you see, this rotation is essentially, you would see that, no, this is dv by dx and this is theta z. So that angle is dv by dx minus theta z. So the angle between, so what it means is, if you look at, so what essentially I am saying, that you have initially undeformed beam and you draw a line normal to the middle surface. Then you apply the load, it deforms. When it deforms, the line which was initially drawn takes some position like this, whereas the normal to the middle surface is like this. So the difference in the angle between the two is actually shear strain. So these two lines, so that means what you are saying, that initially, say at this particular location, you have this line which is parallel to x, this line which is parallel to y, angle is 90 degrees. Now this line becomes a tangent here, so that is actually this line, but this line is now this line, the red line, this particular line, which is now no longer perpendicular to this line. So there is a change in angle between these two lines. So there is now a shear strain there. So we call that strain as transverse shear strain. So whereas in Euler-Bernoulli beam theory, we say that the transverse shear strain is actually 0. So this is the main assumption. Now based on this, we write the deformation. So let us say that the point which was here at y equal to 0 has moved to this particular location. So let us say that this distance is say u0, and that rotation is theta z. And of course, if I take some point here, now that point has actually gone here in the deformed configuration. So let us look at the displacements. So one is the displacement u of any general point. Let us say this point which is at a distance y from the neutral axis. So u0, which is a function of x and y, would be given by u0 as a function of x minus, so this is u0, but then additionally, if you look at the picture here, so you have that green line, dotted line which I have drawn there, a vertical dotted line like this, and then you have that red line which is going like this, and from this if we consider a point at a distance y, so this distance is going to be, this angle is theta z, so this distance is going to be y times theta z, but this is in the negative x direction, so you will have y into theta z. Theta z is a function of x only. That means we are assuming that the rotation is only function of x, independent of x. So still we are assuming that the initially a straight normal remains straight in the deformed configuration. Our plane normal sections remain plane after deformation, but they do not remain normal to the middle surface, deformed middle surface of the beam. So this is, earlier we had said that this theta z is equal to dv by dx, because we said that if you draw an initial material line here, this coincides with the normal to the middle surface in the deformed configuration, so theta z was equal to dv by dx, but now it's independent and different. And of course we are still assuming that v, the displacement along y direction, is only function of x. So that means whether I measure the transverse displacement at bottom, mid, top, or any other point in between, it is same, independent of y coordinate. Of course it varies along x. So earlier, if you remember, of course if we are talking only of beam element with only transverse loads, then this u0 would actually be 0. If there are axial forces, then this u0 will come into picture. So earlier this theta z was taken dv by dx, now we are taking it as an independent quantity. So this is the main thing. So once we understand, rest of the formulation is actually same. So then we talk of strains. So again, strain, if you look at corresponding to x, y and z, so epsilon xx would be, as you know, this is, I'm sorry, This is u, not u naught. That is u at any point xy written in terms of u naught. That is displacement of a point on y equal to 0 along x direction, and then these two terms. So this epsilon xx is del u by del x, which is du naught by dx minus y times d theta z by dx. So this is as usual, no, you write the strain. Only thing is epsilon xx is del u by del x, but u is written in terms of axial displacement of a point on the middle surface and neutral axis, and then y coordinate of any point along y direction. And see, as far as if you look at this displacement theory, you will have actually epsilon yy and epsilon z is 0. But what we actually when we look at this stress displacement stress strain relations, we do not we rather consider plane stress conditions. So for the timing, no, I am just leaving it as question mark, although from this theory, because this would be del v by del y and v is only function of x, so this will actually be 0. Epsilon zz is also I am putting a question mark. We will see how we get it. And then if you look at gamma xy, gamma xy is a change in angle between two line elements initially parallel to x and y. So that is now is nothing but that angle has changed by this much amount from the 90 degrees. So the shear strain is going to be that. Of course, based on the basic theory, you know that this is going to be rate of change of u with respect to y plus rate of change of v with respect to x. And u is given by this expression. So derivative of u with respect to y will give you minus theta z, and of course v is only function of x, so I can write that as dv by dx. So this is what is your shear strain. That means change in angle between two line elements initially parallel to x and y. That angle changes, which is nothing but, no, physically we have shown that it is actually this minus theta z plus dv by dx, change in the angle between the this actual material line drawn here and the normal to the deformed middle surface, that is green line here. That change in angle is actually nothing but the shear strain. And of course the other two planes, the shear strains would actually be 0. So gamma of yz equal to gamma of essentially xz, these would actually be 0. That means in the other two directions, if you take one, we are taking x, this is y, and this is your z. So we are right now considering only the bending in single plane. So there is no change in angle between a line element along x and along z, or a line element along y and z. So those shear strains are actually 0. So this is about the strain. Main thing you see independent quantities are this epsilon xx and this gamma xy. So now let us look at the stresses. So now when you look at the stresses, see, we assume plane stress condition. So plane stress means then what we are saying, that sigma yy is actually negligible compared to sigma xx throughout the beam. Similarly, sigma zz is actually negligible, that is 0. So the moment you use sigma xyy and sigma zz equal to 0, then you get epsilon sigma xx as E times epsilon xx, and which is now, if you write the expression for epsilon xx, this becomes equal to du naught by dx minus y times d theta z by dx. So this becomes your sigma xx. And now from the, since your sigma yy is 0, sigma zz is 0, so you can actually say that epsilon then yy would be minus nu times epsilon xx. So this would actually be equal to minus nu into epsilon xx. Similarly, epsilon zz would be equal to nu, not gamma. So this is minus mu times epsilon xx, and this is minus mu times epsilon xx. So the moment you say plane stress condition, then your strain along y direction is minus mu times epsilon xx, which is sigma xx upon E, and minus mu times again epsilon xx, which is sigma xx upon E for the plane stress condition. If you look at the strains, and of course the tau xy would be equal to g times gamma xy, which is g times minus theta z plus dv by dx. The other shear stresses, that is tau yz and tau xz, they are going to be 0. So you are assuming that throughout the beam, sigma yy, sigma zz tau xz and tau yz, they are 0. Only non-zero stresses are this sigma xx and tau xy. The corresponding independent component of strains are this epsilon xx and this gamma xy. And epsilon yy, epsilon zz are non-zero, but they are not independent, but given in terms of epsilon xx, and these strains and the corresponding stresses are 0. So now let us look at the axial force, shear force and bending moment. Axial force, shear force. We want to write now in terms of these quantities, shear force and bending moment. These are some actually basic definitions, although some of you would actually know this. So the axial forces, essentially if I integrate the sigma xx, so what you are talking about, that if you have a beam and if you consider some cross section, there is certain stress distribution due to axial force and transverse force all put together. You have some distribution, so this sigma xx, somewhere here you have your capital X and Y coordinates. So if you integrate this stress sigma xx throughout the cross section, you get axial force. And let me denote the axial force by Q, or you can use N. Q is axial force. So the axial force, let me put here Q. Shear force we will use as Sy and the bending moment as Mz. So Q is simply the integration of sigma xx over the entire cross section. So sigma xx dA. And we want to write this. So you are integrating the sigma xx, normal stress along x direction, acting on the cross section which is having outward normal along the positive x direction through the cross section to get what is the average force acting on the cross section. And now sigma xx we know as equal to E times du naught by dx minus y times d theta z by dx into dA. And now let us say that origin for y is at the centroid of the cross section. So as you see in this integral, the first term is going to be integration over cross section E into du naught by dx dA, and the second term would be minus integration over the cross section y into d theta z by dx into dA. As far as because u naught is only function of x, so du naught by dx also is only function of x. You can take out the cross sectional integration. Assuming that E is constant within the cross section, the first term would simply be Ea into du naught by dx. Now if y equal to 0 is the centroid of the cross section, that is neutral axis, so then integral y dA would actually be 0. So then your simply Q is, that is axial forces, Ea times du naught by dx. If it is y equal to 0 is not the centroid of the cross section, then this second part will also be actually non-zero. Then the axial force Sy is simply the integration of shear stress. So see, the same cross section you also have shear stress. So the shear stress here, outward normal along plus x, so the positive shear stress is in this direction. So this blue one is actually tau xy. Of course, see, in this theory we are assuming that tau xy, as you see the expression here, tau xy g times minus theta z into dv by dx, and theta z and v, both of them are only functions of x. So we are taking here this shear stress to be constant through the thickness. But you would have studied transverse shear stresses in beams. You find that this is actually not constant, but it has some for say rectangular cross section a parabolic variation. So of course that's the limitation of this theory, that rather than taking actual shear stress distribution which is parabolic, we are taking it to be constant. So sometimes we introduce a fudge factor, we call it a shear correction factor, to account for a nonlinear distribution of shear stress across the cross section. But for the timing, I'm not going to use that factor, as it is based on the theory whatever is coming, I'm going to use that. So then the shear force is nothing but shear force along the y, basically cross sectional force along the y direction. So this is the integration of tau xy over the cross section. And as you see, tau xy g times minus theta z plus dv by dx. So you can write this as g into a, because this tau xy is independent of cross section. So the integration a dA will simply give you the total cross sectional area into minus theta z plus dv by dx. So this is your shear force Sy. Then finally the bending moment Mz. So if you remember, no, that's what we said. We take a small area here and then no multiply by the distance y, we get the moment about negative z axis, but as per our sign convention, no, the positive z axis is coming out of the screen, so the moment, bending moment on this positive face is positive about positive z axis. So when you define this, first you calculate the force, which is sigma xx into dA, then you multiply by the distance y, but this gives me a negative bending moment, so I put a minus sign and integrate it over the cross section. So this is the basic def. This we have actually used earlier. So now if you see again in this, let me put minus here as it is, and then this is E times, you have du naught by dx minus y times d theta z by dx into dA. This is y, you know, that you differentiate between gamma and y. So this is what you have. Now if you see again, if we assume now that y equal to 0 is the centroid of the cross section, so the first integral y dA is 0. So what then you will actually get is integral y square dA, and y square dA integration over cross section is your I, so this will become E I z z into d theta z by dx. See, in case of now from this, if you want to go back to Euler-Bernoulli beam theory, it is straightforward. Now that you can say that no, my shear strain in case of Euler-Bernoulli beam theory, you are saying that no, shear strain is 0. So you say this gamma xy equal to 0. So then you get your theta z is no longer independent, but it's just equal to derivative of dv by dx. So theta z equal to dv by dx. You put everywhere theta z equal to dv by dx, you will get the same equations what we wrote for Euler-Bernoulli beam theory. You know, so here when you put theta z as dv by dx, you will get bending moment as ei into d2v by dx square, the way we did earlier. So this is about axial force, shear force, and bending moment, what we often talk about in these discussions, and this is the relationship of these with the corresponding kinematic variables, that is this the rotation of the normal about z axis, and here what you have is rotation of the normal and a rate of change of v with respect to x, and of course this is the rate of change of u naught, that is actually the elongation or compression of the centroidal axis or neutral axis. So the rate of change of that into Ea gives you axial force Ea. And if there are no axial force, you will find actually that du naught by dx would be 0. And if at any one point of the neutral axis or centroidal axis is fixed, then u naught would be 0 everywhere. So that is when there is no transverse, no axial load. So this is now coming to say equilibrium equations. Now if I look at the equilibrium equations, so I am not going to derive those equations again, but I will just briefly mention you. So what we do, we take a small section of length delta x as usual, we have been doing, and then draw its free body diagram. So the forces are your transverse force, which is say qy, and the axial force, which is distributed force, let us say this is qx, and then the cross-sectional forces. Since we are trying to derive the differential equation, we take this separation between these two as a differential length dx. So I will show the axial force, let us say q here then, and at this end it would be q plus delta q. The shear force here, positive shear force sy here, positive shear force here as sy plus delta sy. The bending moment, positive bending moment here is say mz plus delta mz, and for this line, I think that sometimes this line comes, and this is here mz, right? And now you write some of the forces along x direction, y direction, and moment about z axis, say at any point A here, you can get those three equations. So I am directly going to write those equations. So let us say the first equation is going to be sum of the forces along x direction equal to 0, so that will give you delta qx plus this small qx into delta x equal to 0 will give rise to one equilibrium equation as dq by dx plus qx equal to 0. So this is one. Sum of forces along x direction equal to 0. Now you can check yourself. And then this q is Ea into du naught by dx, so I can write this equation as d by dx of Ea into du naught by dx. This we have just done, that relationship between q and this u naught plus qx equal to 0. So this is one differential equation, say 1. Sum of the forces along y direction equal to 0 will give you actually dsy by dx, that is sy plus delta sy minus sy plus qy into delta x equal to 0 will give you dsy by dx plus qy equal to 0. And now sy in terms of GEA, see that is shear strain, so you can write this as d by dx of GA into minus theta z plus dv by dx plus q of y equal to 0. So this is the second equation. See, this comes from sum of the forces. This is actually from sum of the forces along x direction equal to 0, and this one is coming from sum of the forces along y direction equal to 0. So this is what you get. Similarly, say if I take sum of moments of all the forces about z axis passing through point A equal to 0, you will get this exercise we have actually done earlier. You will get dmz by dx plus sy equal to 0. And if you substitute whatever expressions for bending moment and shear force we have got, we would get d by dx of eiz z into d theta z by dx plus sy ga into minus theta z plus dv by dx is equal to 0. So this is equation 3. So this problem, now these are, see how many kinematic unknowns we have? 3. U naught is one unknown which is a function of x, theta z is another unknown which is function of x independent, and v is the third unknown which is independent function of x and independent of u naught and theta z. So now we have got 3 kinematic unknowns, and these are 3 corresponding differential equations. This is one governing u naught, and this is the governing these 2 and 3 are governing v and theta z, because in both these equations you find theta z and theta z. So these are kind of, you can say, set of simultaneous ordinary differential equations. And when we want to say that we want to formulate the finite element for these, essentially we are then trying to set up the element level governing equations for solving these 3 set of simultaneous equations. So the approach again would be, you can start with weak form. So you write the weak form for this, weak form for this, weak form for this, and you can actually develop your element level governing equations, or you can go through the integral functional approach. Or from the weak form, you can actually get to the integral functional. So I think the derivation of integral functional from these differential equation, I am giving you as a home assignment, and this you should submit Thursday? I think Thursday should be okay. It's not a difficult problem. So I am giving you the assignment of deriving the integral functional, you starting from these 3 differential equations. Starting with the weighted residual statement, weak form, and then integral functional, combining all the 3 weak forms together. Okay, so this you should do and submit next Thursday. So this is an assignment. Derive the integral functional corresponding to governing equations, governing differential equations 1, 2 and 3. Submit on Thursday. Okay, so this is your assignment. Now coming to, so what I am going to do, I will follow a different approach. So let me now write the integral functional directly from the concept of total strain energy, strain energy and potential of external forces. So the integral functional I, how do I write now? I is basically consisting of strain energy, potential of the externally applied forces and internal forces for an element. So keep in mind that this now we are going to do for an element which is finite element, not a differential element. In the previous case, what we had is, this is a differential element of length delta x. So element means it's some part of the component or a structure or actually domain or continuum. And if size is finite, we call it as finite element. Okay. So now here what you are doing is you are considering a finite element which is of no finite length, not as against the infinitesimal length. So with the local element coordinate system here, capital X and capital Y, we call this as local node 1, this is local node 2, and you will have forces, the cross-sectional forces here and here, the distributed forces and so on. So how do we write now the integral functional? First the strain energy part. The strain energy again will be due to sigma xx and due to tau xy. So the strain energy due to sigma xx would be integration over half and then integration over volume. The volume integral I can write integration over length and the integration over cross-sectional area. Half of sigma xx into epsilon xx, sigma xx e times epsilon xx. So it would be e times essentially epsilon xx and epsilon whole square, and epsilon xx is du naught by dx minus y times d theta z by dx whole square dA dx. So this is the strain energy coming due to half of sigma xx into epsilon xx. That is just the strain energy density. When you integrate over the volume, you get over the total structure. Then strain energy due to tau xy, so which is integral again 0 to L integration over the cross-sectional area. This is going to be half, so half I have written tau xy into gamma xy, and tau xy g times gamma xy, so it becomes g times gamma xy square. So g times and your gamma xy is minus theta z plus dv by dx whole square dA dx. And that's all, because the rest of the pairs either the stress is 0 or strain is 0. For example, if you take sigma y, sigma y is 0, although the epsilon y is non-zero. Sigma z is 0, although the epsilon z is non-zero. And of course tau xz and tau yz, they are 0, the corresponding strains are 0. So only these two are going to contribute to the total strain energy, which is this term plus this term. Then of course potential of the externally applied distributed forces. So say you have a force this qy here, and similarly you have this force qx here. So you want to write the potential of these forces. So as we did earlier, integration 0 to L due to qx, this is going to be qx into u naught dx, and due to the qy would be integral 0 to L qy into v dx. This is the potential of axial force, this is the potential of transverse force, that is qy. Then you will have internal forces. And for the internal forces, let me say that I'll also talk about the displacements at these two left and right ends of the element. So let us say that I have in terms of just the displacements. So this is the left end. Let us say u naught is and u naught is taken always positive along the positive coordinate direction. Although the cross-sectional forces would be along the negative coordinate directions, because this cross-section is a negative cross-section. So say this is u naught 1, the displacement of this point is u naught 2. Along the y direction, let us say this displacement is v1. Along y direction, this displacement is v2. Let us say the rotation here is theta z2, rotation here is theta z1. So these are displacements and rotations of these two nodes, say node 1 and 2 of the element, local nodes 1 and 2. So then the potential of external forces, you will have external forces here, internal forces due to the left side structure and right side of structure, you're going to have internal forces here, internal forces here. So that I can, the way we wrote earlier, so let me write it directly, that here at this point your actually q1 is going to be in this direction, whereas u naught is in this direction. So work done is negative, potential is positive. So I am putting this minus sign here. So I'll write, say here first u naught v1 theta z1, u naught 2 v2 and theta z2 transpose, and then all your internal forces. So internal forces are then minus q1 minus s1 is the shear force here, and the bending moment minus m1, then q2, s2 and m2. I think now you understand these terminologies. So q2 is the axial force here, s2 is the shear force in this direction, m2 is the bending moment. Since at this section these forces are along negative direction, so their potential would be positive. So that minus minus finally would become plus. So this is what you get as your total potential energy expression for Timasenko beam element, including no axial deformation, that is axial as well as transverse forces. Of course, as you look at these two terms, we can actually simplify them. So if you do the simplification now, so what you can do, that you can write I equal to the first term. See what you can do here, no open this whole square. So you will have du naught by dx whole square plus y square d theta z by dx square minus 2y into d theta z by dx into du naught by dx. Since y equal to 0 is centroidal, centroid of the cross section, that cross coupling term would actually be 0. So what you will get finally, the first term will give you half integration 0 to L Ea into this. You can just check, you can check yourself. That first one term would be Ea into du naught by dx whole square dx plus another term would be half of integral 0 to L Eizz into d theta z by dx whole square dx. Are you following from here? No, you square, this will going to give you three terms. One is going to be E into du naught by dx whole square. Since both E and du naught by dx are independent of cross section, so the integration over cross section will simply give you A. So that term would become Ea into du naught by dx square. That is what I have written here. Then if you look at the second term is going to be E into y square into d theta z by dx whole square. Y square dA is your Izz, so the second term actually gives you this. The third is, since y dA is 0, y being having origin at the centroid of the cross section, the third term is 0 out of the first one. Then the second is simply because these are all independent of cross sectional coordinate, that is y, they are only functions of x. So the integration over cross section will simply give you A. So plus you will have half integration 0 to L Ga into minus theta z plus dV by dx whole square dx. Is that right? So these are the three terms we get, just writing down the cross-sectional integrations here explicitly. Then the potential of external forces, we can combine two together. So I can write that as integration 0 to L, and first let me write u naught v, and let me also put theta z here, transpose, and then here I have qx, qy, and this I'll put 0 later so that I can use actually H matrix. So this is your dx. It will give you the same, those two terms, whatever I have written here. These two I have written here, like this. When you take transpose, multiply, you are going to get the same thing. And of course the last one, let me now use a notation. So let us call this for the timing, although we are going to justify that. Let us say this vector is actually D transpose, and this vector is, let us say, F internal for the element. So the last part, let me write it as dE transpose into F internal for the element. So this is what you have. Now you can rewrite this further. We can also, what we can do is, although all these three, these three energy terms, strain energy terms can be combined together. But for subsequent discussion on shear locking, I want to keep these two terms. This is, you can say right now the energies if you talk of. So this is the strain energy due to stretching or the deformation of the neutral axis itself, because it involves that du naught by dx. This is actually is referred to as bending strain energy, because this comes from your bending Eiz d theta z by dx. D theta by dz dx is actually giving you the bending rotation, rate of change of bending rotation. So this is bending strain energy, and this is transverse shear strain energy, because this is coming from your tau xy, the transverse shear force, the shear deformation, normal not remaining normal to the deformed neutral axis. So because of that, whatever energy stored is transverse shear strain energy. So I am going to keep this separately, although we can combine, make a vector of du naught by dx d theta z by dx and minus theta z plus dv by dx, 3 by 1 vector we can combine, but subsequently we need them separately, so I'll keep them separately. But these two you can combine, so you can further write these two axial as well as the bending strain energy together, and you can combine them like to du naught by dx and d theta z by dx transpose and then here you have EA0 EIZZ, like we did earlier, du naught by dx and d theta z by dx, and then of course the integration over the entire length of the element. So that's one. So now one is that when you multiply all this, you are going to get these two terms. And now also we have written it such a way that matrix multiplication would be consistent when we replace these by the corresponding interpolations. And the second term similarly you can write half integral 0 to L. GA now, because a scalar one you can write anywhere, and this you can put minus theta z plus dv by dx transpose into minus theta z plus dv by dx into dx, and no rest of the other terms. So I am not going to write all of those. So this is about the various energy terms. Now let us talk of interpolation. Interpolation of, we have basically three kinematic variables. So interpolation of u naught, v and theta z. So what kind of approximation? Interpolation means essentially we are talking of approximation of u naught, v and theta z within the element. So what kind of, now if you see the integral functional, of course when you go through the derivation of integral functional through the Bettel-Riccioli statement big form, you will find in this case the primary variables are u naught, v and theta z. Now these are the primary variables. See, in Euler-Bernoulli beam theory, dv by dx was also primary variable, but here dv by dx is not a primary variable. So from the physics point of view, you can see that actually when we looked at these forces here, so you see as far as derivative of u naught is concerned, it is used to define this axial force. So obviously du naught by dx is a kind of secondary variable because it is relating with the axial force. It's a force quantity. Similarly, if you look at here, d theta z by dx is used in defining bending moment. So it's basically again representing bending moment. So d theta z by dx is kind of secondary variable. Same way, if you look at here in the expression for shear force, here you will see that this minus theta z plus dv by dx together, they are coming and defining the shear force. So you see, although theta z is coming together with dv by dx, but if you see dv by dx alone, it is coming in defining the your shear force sy. So it's now no longer a primary variable. If you look at the differential equation, their weak form, you will also conclude that u naught, v and theta z are only primary variables and their derivatives are actually secondary variables. So then based on the requirement for the finite element interpolation, we will have to maintain the continuity of primary variables across the element. So what we need when we talk of element, minimum what we need, say 2 nodes, and at each node, say this is node 1 and node 2, we should have u naught, v and theta z as degrees of freedom. That is what I had sketched here, although at this point I had only sketched it for the purpose of writing the potential of these internal forces. But I have to have u naught as a primary variable, degree of freedom here, degree of freedom here, v as a primary variable, a degree of freedom at first node, at second node, theta z here, theta z here. So at each node now I have 3 degrees of freedom, 2 displacement and 1 rotation. For the element, total we have 6 degrees of freedom. Out of those, u naught 1 and u naught 2 are corresponding to u naught, v1, v2 are corresponding to v, and theta z1 and theta z2 are corresponding to theta. So that means with this 2-noded element with these primary variables has degrees of freedom, when I go and interpolate u naught, so I can take u, because corresponding to u naught for the element I have only 2 degrees of freedom. So in the approximate solution I can have basically 2 unknown constants. So I can assume this as a0 plus a1 into x. And now when you write a0 and a1 in terms of this is your local element x-axis and the element length is say small l. So you can write a0 and a1 in terms of u1 and u2. So you can finally write this as the same shape functions, n1 into u naught 1 plus n2 into u naught 2. This exercise we have done earlier. It's the same thing, that u naught 1 is equal to a naught and u naught 2 is equal to a naught plus a1l. Solve for a naught and a1, put here and collect the coefficients of u naught and u naught 1 and u naught 2. This is what you get. And where n1 is nothing but 1 minus x by l, and n2 is x by l. So now in this case you will see similarly, you would see that no, you can write V as n1 V1 plus n2 V2, because corresponding to V also within the element we have no 2 degrees of freedom. So I can take the solution of the same form, say B0 plus B1x, and when we write a B0 and B1 in terms of V1 and V2, this is what we get. These interpolation functions are same. So same way theta z would be n1 into theta z1 plus n2 into theta z2. So now see, earlier in case of Euler-Bernoulli beam element, we had to interpolate u0 no like this, but V was interpolated using a cubic polynomial with 4 unknown constants in it. But now here we are interpolating V only using linear polynomial, say B0 plus B1x, and same, but then we also are interpolating here independently, this theta z. So I think I'll stop here and we will continue in the next class. So work on your this assignment, as well as again think of why we are taking this interpolation for this particular case of Timoshenko beam element. So we'll continue further development of element level governing equations in the next class. Any doubts?